So we're going to continue the stuff that we've been working on. Okay, it's even a little more complicated than that. I know, one more. All right, so we're going to look at a problem today where we're not revolving around the x-axis anymore, or the y-axis, but we're revolving around some arbitrary line. Okay, some arbitrary random line. The axis is an arbitrary line for sure, but what if it's not the axis? That's what we're going to say. So, did I print what? No, we're only going to do really like one major problem actually. We might have two in the end actually. So, let's think about this for a second. So, imagine what I'm showing you here. If I take this piece of paper, it might help you to look at this to see what we're doing today. If I take this piece of paper and I were just to sit here and revolve it like this, take the paper and revolve it 360 degrees, I would get a cylinder out of it, right? I'll get a cylinder. But what if I revolve this paper around a line that's over here now? A line is over here. Okay, a random line is right here, an axis of rotation. And I take this paper and I revolve it around that line. What kind of a shape am I going to get? A thin like shell, right? Or a hollowed out cylinder. So again, taking this, revolving around its own axis, I get a cylinder. But when I move it around some other random axis, I end up getting another shape.
Oh, they could use this axis.
Oh, thank you. So here's our axis. So when I revolve it around this axis, yes, I'm going to get just a cylinder. But when I go around like this, I'm going to get this shape that's hollowed out. Not only is it hollowed out, but it's taken up, isn't it a longer path for me to go from here all the way around, as opposed to me just going around the inside? Right? If I just rotate it around this inside, it's a pretty short path. But when I have to go all the way around here, this is a long path. Therefore, if I think of this as a circle, wouldn't this be a bigger circle with like a very big radius or a very big circumference? And this would be like a smaller circle from bird's eye view? So what's going to happen is this. Whenever we have a separation between the object we're revolving and the axis of revolution, we're going to end up getting a larger volume. So if I were to just simply take this and revolve it around the meter stick, I would just get a cylinder. It would sweep out a cylinder. But the minute I do this, I revolve it all the way around here, and I go all the way around the outside, come all the way back around, I get that shell, and the volume is much larger. So that's the first thing you want to make sure that you know. If you revolve around another line that's a certain distance away, that volume is going to become larger. It's going to become greater. And yes, you're going to have that hole in the middle, or that hollowed out part. And that's what's happening here. So let's take a look. Determine the volume of the solid obtained by rotating the region bounded by the first function and the second function. And we're going around the line y equals 4. Y equals 4. So we're no longer revolving this around the x-axis. It's not just the x-axis that's rotating, but we're also going around that line now. So let's go ahead and start by graphing this. X squared minus 2x. If I were to graph that one just analytically, what's my y-intercept? 0. Right? My y-intercept is 0 for that first one. Good. Now, if I continue that, how do I know what else to do with this? What is it really just going to look like? Yeah, kind of. But guys, we're looking at this one, guys. Not that one. Come on.
So the
parabola. What about that minus 2x though? What is that going to do? Really?
It's gonna affect this concavity.
Yes, absolutely. Affect this concavity. Its shape. Absolutely. Good word. So normally y equals x squared is just a parabola. We draw like that. This would just be a parabola that would be more concave up. Okay? Its concavity would be greater. So that's the one we're going to look at really. Not that it matters right now because y we're just sketching. It doesn't really matter because we're just sketching. So that's that first part right there. And y equals x. Y equals x. What is that going to be? Just a line. But how do I know whether it's on top or down below?
It cuts in between the first quadrant.
At what kind of an angle?
45.
Very good. A 45-degree angle. Remember, guys, the line y equals x is just simply a line that goes up 1 over 1 every time. So that's my line y equals x right there. So here's my two curves. And I want to know if I take the region bounded by, what does that mean, the region? Area. Always put those two words in. So here, if I want to know the region bounded by these curves, this is the region bounded right here. Okay, that's our region right there. So now, in class today, what we did was we revolved this around the x-axis, and we also did it around the y-axis last class. So we've done both of those. But now it wants to be revolved around the line y equals 4, which is where? On the y-axis, good. It could either be right in the middle, it could be here, it could be up here. How do I know where it is?
Plug in x, plug in 4.
Okay, what should I do? I should really find the intersection first. Very good. If I can find this intersection, because again I'm sketching, remember I'm sketching. If I can find this intersection, I can see what height this is, and then I know where 4 is along my y-axis. Because I don't know if y equals 4 is up here, if it's down here, if it's down, I mean I know it's above the axis, obviously, it's not negative. So, find that intersection to start. Clearly, what's this intersection? 0, 0, which makes sense. Plug in a 0 for both, you get 0. Find the other intersection. So let's say x squared minus 2x is equal to x. That's our first step. What do I do with this x? By doing what? Adding. Subtracting x. Okay, again, subtract x, subtract x. Okay, basic algebra there. Now I factor it out, what do I get? Well done, 3 and 0. So my roots, or my intersections, my roots of this polynomial, but my intersections are 0 and 3. So this coordinate is 3 comma something. Now it actually is important to know that y value. Remember today I was like, it doesn't really matter? You didn't need it before? You didn't. But if I plug in a 3, what's the value of y? Just 3. Plug in a 3 here. 3 squared is 9. 9 minus 6 is still 3. So this is the point 3, 3. So now I know where to draw my sketch. Okay? So again, y equals 4 will now be up here. That green dashed line along the top. So think back to the example we looked at today before the end of class. The one we had today was this one that we're looking at. This is the one we're doing right now, actually. And that's that line right there. So this is 3 comma 3. Oops. This is 3 comma 3. This is 0 comma 0. Now, notice this went below the axis. You see how that went below the axis? When we drew it, did we draw it below the axis? We didn't draw it below the axis. But it's not going to make any difference, actually, at all. It's not going to make any difference whatsoever. And I'll explain why in a second. Okay, again, you know why already? Because it's a sketch, sure, absolutely. But why does it not matter? What am I going to do when I revolve? What do I care about when I'm revolving?
Just if it's revolved around
the what? The inner and the outer what?
function.
Curve, good. And what do we call it though? We squared it because it was the radius. Radius. All we care about is the inner and the outer radius. Now, the tricky part here, let's see if he discusses it on here.
We discussed it.
I don't think he does a good enough job of it though, that's why. Yeah, it's not really that good of a job of discussing. All right, let's go to this. Let's take a look. Now, if I want to revolve this around this line y equals 4, I'm going to be revolving it up and around. Everybody see what I'm doing now? Again, if I were revolving around the x-axis, it would just loop around here. That's all it would do, it would loop right around. But I want to revolve around that axis y equals 4. So, for this kind of a problem here, the tough part is to remember what is the inner radius, what is the outer radius. Which of these curves is closer to your axis of rotation?
The y.
The linear function. Linear, right? So let's highlight this in black for a quick second. That is going to be my inner radius location. But it's not necessarily the inner radius anymore, and that's where you have to talk about now. So I want to know the inner radius, since I'm revolving around this random line here, the inner radius is that distance right there. Again, this is my axis of rotation. That is my inner radius right there.
Oh, nice.
How do I represent that, though, algebraically? That's the tough part now. How do I know that distance? Because I don't know what that distance is.
Y plus 4.
Where are you getting y plus 4?
Because the origin of the y-axis is 0, so it's raised up by 4.
You're making a little mistake there along the way. You have a right idea. A little mistake, though.
Is it any point? But the distance can be different.
So it's going to change, absolutely. It's going to change. So we have to represent the inner radius as a function of my upper curve. Absolutely, you're right, Karen. So what is? How can I write an algebraic representation of the inner radius?
It's just the inner function.
No, it's
It's just the inner.
Houston. The height of this function. Say the height of this function here is 6. Oh, it can't be 6, obviously. Let's say it's 2. Let's say the height of the function here is 2. Okay. And then what is this distance that's left over then?
3 plus 1.
Oh, people, come on. 2. What is the height of this line here?
Four.
This is the line y equals 4, right? So if I knew that this height was 2, what would be left over? If I knew that this height was 3, what would be left over? So what am I doing to get those values?
Plus 1 and plus 1.
Adding k value.
I'm subtracting 4 what?
4 minus.
Okay, but use your function. 1. What's the function?
4 minus x.
4 minus x. 4 minus x. Again, let's go through this. If I want to know this function here, the height of this function at any point in time, the actual height from the x-axis, the actual height of any of those black lines is represented by the function y equals x. Remember, the function is y equals x that was given right here. That's the height of this. Stop talking, please. That's the height here. Now, the entire height here is 4. So if I want to know what's left over for the inner radius, I got to do the whole thing, which is 4 minus off whatever this is. This is always x. That's this function right here. So if you want to find the inner radius, you take the axis of rotation here, which is 4, and a lot of this, guys, there's no formula to it. You have to actually inspect every time. You can't just write a formula that still works every single time, because it depends on where the axis is. If the axis were down here, it'd be totally different. If the axis were a vertical one, it's totally different. So you have to analyze this problem every time. So the first thing that's the toughest part here is to recognize what your inner and outer radius are. So the inner radius is going to be this distance 4 minus whatever this is. This distance 4 minus whatever this is. Inner radius is this distance 4 minus whatever this is. Well, whatever this is the function y equals x. That's what this distance is here. Every time. So your inner radius is just a whole 4 minus off whatever's not there from the function.
So then for the outer one, it would be the function of that x squared minus 2x minus that.
Yes. So again, wait, say it one more time. One more time, Karen. I think you made a little mistake there along the way.
What?
You have to sort it by the
And
big.
you say minus 2x.
So they're saying.
You're asking about the outer radius, right, Karen? Okay, the outer radius is, let's just draw this so we can see, the distance from the axis of rotation to the curve. The distance from the axis of rotation to the curve. Anywhere along the way. That's my blue line. That's the outer radius, right? Now, how can I express that algebraically?
Wait, what?
The blue one.
Minus 2.
4 minus x squared.
Monica Ramirez, please come to the front office. Monica Ramirez,
Why is
please
it
come to the
the
front office.
Oh, cool.
I don't know where you're coming up with this other one. Here, let's go through this again. The full distance from here to here is 4. If I want to get rid of this little piece right here, this little piece right there, I know that this little piece is represented by the function x squared minus 2x.
Yes, it's 4 minus.
So it's going to be 4, which is the whole thing, minus off that little piece will give me what's left for the outer radius. So this is 4 minus x squared minus 2x quantity. That's the hardest part about revolutions, really, is figuring out what your inner and outer radius is. But now, it's the same problem as last time. It's no different whatsoever. If you want to find the volume now, the volume is the integral with pi in front. We'll put the limits in a set. Oh, we know the limits, 0 to 3. Of the outer radius, which is this one, minus the
Square
inner radius. So we've got, you have to do what? Yes, come on. The computer sometimes, or the smart board gets a little freaked out. So it's the outer radius, again, the outer radius squared minus the inner radius squared. The inner radius happened to be 4 minus x dx. Okay, it's a lot of work to do. This is not an easy topic. That's why I'm trying to keep emphasizing this. It's just worth a lot of points in the test, so it is worthwhile to go through.
So Mr. I have a question. So say you basically, so on the test they're gonna say that like that's 4 and the line is like a certain distance away. Okay.
So-
So they're gonna tell you like that's 4.
And they did. It says, about the line y equals 4. That was the beginning part.
Right.
Houston, follow-up question. What if the line hadn't been y equals 4? What if the line had been y equals 7? What would have changed in my problem, Houston?
To 4.
To what?
4 to 7.
Why?
Because it said that the line was 7.
Okay, but without just memorizing it, replacing it. Think about it logically, right? If I had a line like y equals 7, it would be up across there, right?
Uh-huh.
How much further up would that be? What would that make the inner
spots
radius?
up.
3 spots up. So it would increase the value of my inner and outer radius by 3. So instead of this being a 4, that's why it's a 7. It's increasing by 3.
Okay, but like in the question, we won't even have to look at the graph. The question say y equals 4, so we'll know that. 4
Yeah,
is
but
what
the
we
thing
do.
is, I would recommend you draw or sketch the graph, because just doing this problem without a graph,
Oh, no,
very
I'm
difficult.
going to use graph. I mean, in general, you know that is what you're going to be using. You know what I'm
yes,
saying?
as your
Yeah,
upper
fine.
bound, as your upper bound, yeah.
Yeah.
So if this had just said part B, it said now try for 7, you could just put 7. Yes, absolutely. Okay. Let's do another example. Again, I'm going to leave this alone because this stuff that's here, you can do this in your calculator. Type this into your fint or into y1 and do the integral from 0 to 3 and then multiply it by the pi. Okay, I'm going to leave that alone just because of the fact that we want to go through the problem and the setup. The setup is the most important part here. Again, the setup is the toughest part. Let's look at another example. Yeah, the limits and the setup themselves are worth 2 points. The answer itself is just worth that 1 point. So 2/3 of it is knowing from go from where to where, or 1/3 is going from where to where. Another third is knowing which is the inner and outer radius. Okay. What if we have, let's say, y equals. I printed out a bunch of examples for you guys. Actually, to make it easier. Give it 1 second. Let's first do this. All right, let's take a look at two functions. If we have the volume generated by y equals x squared and y equals 4x minus x squared. And we want to revolve it around y equals 6. So I want to take the region that's encompassed by these two functions, whatever that region may be, R, revolve it around the line y equals 6.
Yeah, I have a question.
Mhm.
So you say y equals 6 when we know that we revolve it like this way?
Yes, now assuming it's below. Assuming the region is below. What if the region is above? Then it comes around down like this, right?
Oh yeah, I'm just saying like it goes like you reflect it like horizontally.
Yes, you revolve it horizontally.
But if it say x equals 6, would you revolve it?
Like that,
Alright,
yep.
yeah.
Just like the y-axis versus the x-axis. So y equals x squared, we all know what that looks like by now. That's that function right there. Okay, that's the first one. 4x minus x squared, though. 4x minus x squared. Right away, it's going to concave down, right? Because my leading coefficient is negative here, so it's definitely going to be aimed down. And then if I want to just test this, if I want to just test it, the first starting point would be 0, right? It'd be right here. What about 1? Just type it, do a 1 in your head here.
I know 2, 3.
3, right? So 1 is at 3. So this graph is going to be right here at 3. So 1, comma 3. If I wanted to do this in my head as a sketch. Again, when I plug in a 1 here, I get 4 minus 1, which is 3. So this coordinate is 1, comma 3. What if I plug in a 2 for x up there? Why? 4 times 2 is?
3.
Minus 4 is? Good. So 2, comma 4 is the next point I'm going to have here. So I'm going to see that, what is that, what intersection point is? Okay. I'm going to notice that here, when I get to this, so this should be a little bit steeper. What you'll see here is I'm going to get this right there. So we're going to have a graph that looks like that. And then it's probably going to come back around. Let's see. Yes, it's going to come back around. It's going to go through at 4. Is that going to be a maximum on the graph? Anybody look at the actual graph yet? Maximum location? Well, it's here the derivative.
Yeah.
Negative b over 2a. Negative b is going to be negative 4 over 2 times 2 is 2. Yeah. Good. All right, so that's going to come back around and cut through like that. That's my second graph. This is my y equals x squared graph, and clearly it doesn't matter on the left side, but we'll draw it. So where's the region again? Here's the region right there. Okay? That's the region we're looking at.
These are all calculated problems.
They're all what?
Calculated problems.
The majority of them for the AP exam are calculator problems. The only one that I saw that was not, the only one, there was a multiple choice on the 97 exam. I think it was number 25. And it was a multiple choice, it was a non-calculator. But the function was so simple. It was like, revolve y equals x squared around the y-axis. That was it. And you know y equals x squared, and you have to revolve it this way. So you have to solve for x in terms of y, use dy instead. It was a very basic one. It wasn't something like this. Okay? Now, the line y equals 6, let's draw it. It's going to clearly be above the graph in this one. There's that line. So I'm taking this solid region or this area region here, and I'm revolving it around that line to make a solid. Okay, I'm revolving it around that line to make a solid. So, 5, 6, this point was 2, 4. Okay, there's my intersection. My other intersection is 0, 0. So does this problem look familiar? It looks like the last one, doesn't it? We took a region below an axis and we revolved it around it. So if I want to know what the inner radius is, the inner radius,
I got you. I can do this.
okay?
Inner radius is 6 minus 4x minus x squared.
Awesome work. How do you know that?
Could you just learn? Oh, because it said it was 6.
Okay, so the entire height is 6, right?
Yeah.
And we want to know just the inner radius.
Subtract it, yeah, the inner radius.
So I need to subtract that right there, right?
Yeah.
So again, if I look at this, the distance from y equals 6 to the x-axis, that full distance is 6. That's the 6 right there. But I want to take away this little portion, so I'm left with the inner radius right there. This portion is represented by the height of the green function. The green function on the graph here is this function that we had to begin with. Next, yeah?
Instead of writing the whole function, at least some point just say writing y1, y2.
I guess so bad,
Just like,
Sure, on the test, you mean?
think, yeah.
If this is given as g and this is given as f,
In general, just like instead of writing so much, just
you can write your answer as a setup for an integral as 6 minus g and 6 minus f if you'd like to. That's no problem. Provided they're given that way. If they're not given as, you know, f and g, which they always will be given that way.
Yeah,
So you have to work. You have to label them. But they should be always given that way. I've never seen where it's not. I mean, y1 and y2 maybe they'd call it, but I doubt that. All right, that's the inner radius. Now I want the outer radius. Somebody else besides Houston? That's the outer, not R2. The outer radius is from here to here now, but I don't want this little piece right here.
she said it.
Y 6 minus x squared? What am I trying to get rid of? What is this little piece? What is this height of this function? It's the red one, which happened to be? X squared. Very good. Again, this entire distance from here to here is 6. But I want the outer radius. I want from here to right there. So this distance right here is the whole thing 6 minus off this little piece. This little piece is the red curve. That little piece that's the red curve is x squared. So the outer radius is 6 minus x squared. You don't need the parentheses, but I'm just putting it in. Okay? That's my outer, my inner, and at this point in time, all I got to do is apply the formula. So the formula is what makes it a little bit easier. It's finding the inner and the outer radius that make it tough. So I've got the volume equal to, could somebody step me through this? Pi, continue.
We don't have a, we do?
We have our thing, 0 to 2. Look at your graph. The intersection went from 0 to 2.
Oh,
Remember, who was it? Edgar, right? Pointed out that the intersection was 2, 4 on his calculator. Okay. If you want to solve for it, though, what do you do, obviously? Set them equal, okay? You would get that 2, and then if you plug a 2 back in, 2 squared is just 4. Sorry, continue, 0 to 2.
x squared minus
Square square.
minus 6 minus 4x minus 6 squared.
Okay? Same thing as last time. The problems aren't changing, guys. They're not changing at all. All that matters now is that we have another random arbitrary line that we're revolving around. Now, what if we look at...
-6.
Oh, we could try -6. We could try -6, absolutely.
So kind of thing with any problem, just choose the balance.
Okay? Change the balance, fine. That's what your homework is going to be. You'll see that you have to do it around random different
Doesn't
lines.
RI and RO switch?
Yes. Very good. So let's discuss before we assume that.
What do you say?
If we have now the same function, I'll redraw it so we can see that.
So when the line's on yours, one on the way. Oh yeah, because the inner is on the other side.
What was this outer function? This was x squared, obviously.
That was
4x minus x
squared.
Thank you. Okay, there's my region right there. These continue, obviously. Now, instead of revolving around 6, let's try a random number though, -3. Okay, just so we avoid the 6 again, same problem. So if I go about -3, okay, I revolve around -3 now. Revolving around -3 now, what Edgar noticed right away is that your inner and outer are going to actually switch now. And you'll notice that because if you want the inner radius, you start at the axis of rotation and you go to the first thing that you meet. That's the inner radius. If I want the outer radius, I start again at the axis of rotation, but I go to whatever the second thing is that I meet. That's my outer radius. That's my outer radius. So, you can either do this by looking in geometry, which is what I really do, or you can memorize what to do. Either way works. I would recommend that you just look at the picture. What is this distance right here? But if I'm looking,
Oh.
I want to know what the actual radius is, though. So what is the distance, not the displacement? See, that's where physics will come in to help you. What is the distance from here to here?
6 plus
It's just 3. The displacement is -3. I know, it sounds weird. Because are we trying to figure out the length of the radius, Kerry? So if I want to know what the length of the inner radius is, it's going to be this 3, right? Plus whatever that little part is there. Well, what's that little part? Which function is that? X squared, isn't it? So really, it's just going to be 3 plus x squared.
That's what I meant before. I said 3 plus.
Okay. Now, the way your book will teach you to do this is to take this x squared, and they'll say minus the lower part.
That's what I was thinking.
That's
But minus the negative is still what? Yeah, the book is going to say x squared minus -3. They're going to say take whatever bounds the inner radius and subtract this from it. You're taking the upper minus the lower again. That's the idea. But I'd rather you guys understand what's going on. It's much easier to do it that way. Because when the problem changes, it can totally screw you up. So the book tells you to take
No, not
what I tell you to take. Okay, find the physical distance. How far is this apart? Right here, here. 3, and then whatever this gap is, that gap is represented by x squared. That's the inner radius. Absolutely. Now, outer radius. Oh no. Outer radius. It's definitely 3 again, right? We all see that? Outer radius is 3, and then I go all the way up to what?
What's up, Jingle Bells?
So the inner and the outer radius.
You can hear him.
The inner and the outer radius here are easily attainable from this part. Okay? Again, the whole idea here is this, guys. Please don't memorize this stuff. It really doesn't help you. Especially when they give you some arbitrary random function they call f, and they don't even say what it is. They'll just say this is the height f. Then you have to realize you have to take 3 plus, for this one, if this was f, it would be 3 plus f. If this function were called g, it would be 3 plus g. Right? Isn't that what we're really doing there? Again, this function here, if I called this f randomly, I would just replace that with an f, right? If I called this function g and I didn't have a function for it, I would call that just simply g. And if I knew that g and f intersected, if I knew their location of intersection, which I do here, if it was given in the diagram, I don't even need the equations to set up the integral. Again, the problem here a lot of the time is just set it up, that's it. If they ask for a number, it's usually a calculator problem to calculate. So, obviously we're not given that, so let's get rid of that stuff that was up there. Okay. Now, let's come up with an expression that gives me the volume here. Using my inner and outer radius. Somebody else besides the person who did it last time, I think it was Christian last time.
Isn't it pi? Pi. I know it.
What always goes in the front, everybody?
Pi.
Pi. All right. So we start with a pi.
Yeah,
Okay. And I integrate for my limits. Where am I going? From where to where again?
Yeah.
Good. The x coordinates, right? Because I'm revolving this way. I'm revolving around something that looks like the x-axis. Next. Silence, please. After that, what goes on next?
3
Outer squared minus
Inner
inner square. Very good.
dx.
Very good. Outer squared minus inner squared dx. Now, I would I would drop the parentheses
Yeah,
here.
you didn't.
Okay, I would.
Oh,
Can't you just
man.
Yeah, I could just switch the signs, but I don't want to confuse anybody. Thank you, Karen. You're right. So again, when I do this though, guys, please take a look here. Does this parentheses set in blue really matter?
No.
It makes no difference actually, because there's no minus sign here. Had there been a minus here, I'd have to make sure I negate both of them, but it doesn't matter in this case. So yes, it's outer minus inner. Outer minus inner dx. Guys, and by the way, I heard somebody say, does it really matter? It's assumed. You're right, whoever corrected me there. We need a dx there. You have to have it there. Because if you don't have a dx, then I don't know what I'm integrating with respect to. And on the exam, without the dx, you're not going to get credit for the setup. Again, I'm telling you right now. You'll get the point for the limits. You'll get the points for the limits, but the integrand needs to have a dx next to it. Or else I don't know what the integral is anymore. Now I don't know if I'm integrating x, y, z, it doesn't matter. Now I know it's x.
Well, why would you be integrating y?
When you get to calculus 2 and 3, you're going to see that you have that. You have dx's and you have y's in the problem, actually.
There's no y.
I'm just telling you, it's just nomenclature. If you have a dx here, you could technically have a y in there. In this case, we don't. You're right. But you could. So I'm trying to get used to it, because you're going to see it so
Wouldn't it be considered just a constant?
Or you integrate both sides?
It's constant. Now, when you get to calc 3, you do what are called double integrals. You integrate 2 times y's and x's. That's where it's going to get a little tricky. You have a dx, the end will be dx, dy.
Kill your patience.
All right,
The wrong dosage, not.
last one, people, last one.
Like I had my
Isn't
fears.
that bad?
Yeah.
And that's the one that-
And one day you're coming to the point.
My child is
That's the one that-
Why math? One half is
That's what it is there.
That after school is still giving you extra there, right?
supposed to say lies, but it's supposed to matter to a
Well, yeah, after school is still giving you that.
What?
The after school, especially for history,
Oh.
still gives you extra no matter what.
All right, so we got
That's part of like always kept you
we got y equals square root of x. We've got the region y equals 0, x equals 3. And we want to take the region that's formed from these three forms here and revolve it around the line x equals 6. Okay, and you know what the hardest part here that people confuse? The actual setup here. A lot of people get confused on what's going on right here. What is the line y equals 0?
Just the line on the origin on the y-axis.
Ooh,
No,
you
no,
know
no,
that.
it's on x-axis.
It's on the x-axis. Be careful.
Horizontal.
The line y equals 1 is here. Y equals 2 is here. Well, where's y equals 0? It's right here. So this is pretty much the x-axis. So they want you to integrate between the x-axis. I'm going to put it here still.
You're right, we use all colors.
The square root of x. Does that ever have a negative component? No. The graph of this is my simple curve. By the way, I was doing this today in Algebra 2, and it was nice because I was able to emphasize and show them where it actually comes up. But when are we ever going to use this? I'm like, a lot of the time it does come up in calculus because you're taking square roots of stuff. That's where that function is coming out. Well, some of them are going to take calculus. So, that's that line, and then what is it, Kenny?
A vertical line.
At x equals 3. Very good. So there's some vertical line here at x equals 3. So there's my region right there.
I wasn't even in class, my God.
Okay? Again, I have to specify.
I'm hungry.
I'm not going to burst your bubble, but I hope you get that. I have to specify the x-axis because if I didn't, all this under here would be shaded, right? Everything would be shaded forever. I don't know that the x-axis is a boundary until I see y equals 0. The y equals 0 tells me that the x-axis is a boundary, this is a boundary, and this is a boundary. 3 boundaries give me like a, a peninsula-looking shape, just a closed figure. Okay? So that's my region R. Now, I want to now take this region and revolve it around the line x equals 6. X equals 6. Before I even get there, though, what's the line x equals 6
What
look
about the
like?
other two?
It's a vertical line. A vertical line. Okay, here's 3. Here's 6 out here. So what kind of revolution am I doing now? Around the y. So I'm going to have to do everything in y's and dy's and my y limits here.
Why?
Why am I?
Well, why not?
But that doesn't matter, does it?
Okay.
It's just a different letter.
Why?
But why don't you put the other functions up?
Just makes it a little tougher. All right, so this is my radical x function here. Okay, that's my radical x function there. Y equals radical x. This is the line again. X equals 3. Now,
Can we solve them all?
before we go any further, I want to talk about conceptually first. If I take this solid, or this area, and revolve it, I'm revolving it like this, right?
Yeah.
So I'm going to get that like kind of disc shape again, with an empty in the middle. More of a washer than anything.
Yeah, it's like one of those,
It is like one of those cakes, actually.
yeah.
What are those cakes called?
Bundt cake.
Bundt cakes. It's like a bundt cake, or you can think of a funnel cake is more like a bundt.
It's a
Bundt
No,
cake.
B-U-N-T.
Yeah. A bundt cake. It's actually, it's a cake that has like, a bundt cake actually has like a curve on the hole.
Yeah.
Yeah.
But no, he was right. A donkey.
Right.
A donkey bowl?
Now,
Dog bowl?
stop. Come on, guys, focus. Here, the tricky part is knowing what the radii are, the inner and the outer. So if I'm revolving around this axis, I start at the axis,
The prom committee meeting.
I go over to here,
Carolyn, room 204.
and I see that that is my inner radius. Everybody see that?
Yeah.
Again, so my inner radius is represented by a vertical line, x equals 3, it looks like. That's the confusing part to start. We're clear on that so far?
6 minus 2.
Okay, the inner radius is whatever that distance is. What is that distance always going to be, Edgar? 3. No matter where I put this, watch. If I put the inner radius here, if I put the inner radius here, what is that distance always going to be? 3. So the inner radius is legitimately just 6 minus 3. That's what the inner radius is. It's the whole thing, which is 6, minus this piece, which is 3. So the inner radius, we could just simply list this 3.
Mr. Howard, what about at the bottom?
No, I think, doesn't that matter? No y equals 0?
What are you talking about at the bottom?
Bottom right is right. Doesn't make a difference. The bottom function.
It's 0.
No, you're confusing yourself with x and y. Let me keep going for a sec, because we're running out of time
The
here.
y equals 0 part.
So,
The y equals
And
0.
x equals 6.
yeah, we don't need to worry about that. That's going to come into our limits. Hold off. Let me just keep going, please. I'm doing this for a reason this way. The outer radius is the next thing that it would intersect with. So I start again at the axis. I go over until I get the next intersection, which is right there. Or if I do it from here, I go over and I get the next intersection right there. So for my outer radius, the whole thing is 6 minus off whatever this distance is here, or whatever this distance is here, which is that function, right? Now, the tough part is I want to say it's radical x, right?
You said because it's y.
Yeah, we're running this way, guys, so we have to solve for y. So
Y squared.
y squared is equal to x. If I solve this, square this side, you get x equals y squared. So when I'm revolving this way now, I have to think about that this is 6, minus off whatever this is, which is y squared. So the outer radius is 6 minus y squared. Now, the next part is to know what are my limitations for my integral. Because I'm integrating at the end with a dy. So my limits have to go from some lower number to some upper number. What is this lower number now? 0. That's where the y equals 0 is going to come in. Remember you asked about that? I was trying to wait on that. Now, the next thing I have to know is this. What is the y coordinate right here?
I would put like kind of.
What is the y coordinate right here? I got it. Say it.
3.
Stop 3.
The wide one.
Right here, what is it? The square root of 3. Think about this function, guys. This function is defined as y equals radical x. So if I know the x coordinate is 3, which it clearly is, if I plug in 3 here, I get radical 3. That's the y coordinate right there. Again, I take the x coordinate, which is 3, plug it into the original, tells me the y coordinate is radical 3. So now I'm integrating from 0 to radical 3. Again, remember, when you revolve this way, your limits are your y coordinates, and you have a dy. Now the outer radius, 6 minus y squared, quantity squared, minus the inner radius, dy. Again, It's the same every time, it hasn't changed. It's always outer radius squared minus inner radius squared. The inner radius happens to be 3, so it's just 3 squared. The outer radius is that 6 minus y squared, the outer radius squared. The tough part for students on this problem is knowing that you need to do the dy, because you're going this way, knowing that your limits go from 0 up until radical 3, whatever that y value is. Okay, tonight, here's what I want you guys, or you have 2 nights, but here's what I want you guys to do. I circled 4 problems on here for you to work on. I didn't put them on your worksheet, I circled them on your worksheet, so circle these right away, please. So, tonight I want you to try to number 3, number 6,
I can't even think for you.
let me see number 3 on your page, hold on.
6.
Y equals radical x.
Yeah, the function for number 3 is y equals radical x. Everybody, if you want to write it down now, for number 3, you can't really see number 3 that well, it's y equals radical x. So number 3, number 6, number 12, which will take you a while because you have to do 4 different rotations there. Okay, number 12, and then number 14. Well, look at number 12. They want you to revolve around the y-axis, the x-axis, a horizontal line y equals 8, and then the vertical line x equals 2. So you have 4 volumes for number 12, but the idea is that you should be able to pick up after a while how they're going to alter. You'll see patterns in there. So 3, 6, 12, and 14. Okay, there's a lot of problems. I'm telling you guys now, this is easy points on the test if you practice. This topic specifically is all about becoming familiar with it. If you know how to do this every time, you'll be golden. Okay, on Thursday, we're going to look at something with volume again, but it's a little bit trickier, just to give you a preview. Who's not here today, just so I know? Rosie. Where's Rosie? Hey, can you talk to her outside of school? Tell her to email me, please, why she wasn't here.